we had a change in program. Ashutosh will give the next talk now already, and then as far as I understand, Erka will give the last talk, and we will only have one talk after a coffee break, please. Okay, good, thanks, please.
Okay, thank you to the organizers for letting me speak, I guess. I'll be talking about smooth min-entropy lower bounds for approximation chains. This is work with my supervisor, Frederick B. Unfortunately, we haven't yet put this up on archive. It will be up there soon. But if you want to follow along in details, it's on my GitHub. A preprint is on my GitHub. Go for Ashutosh/approx chains. You can have a look. All right. So let's begin with some definitions. I guess everyone here would know what the min-entropy is, but it's defined this way. The smooth min-entropy is just the supremum around a epsilon ball around rho. And the importance of this entropy really comes from the leftover hashing lemma, which says that the amount of randomness which one can extract from a register is when the adversary holds the conditioning register is equal to the smooth min-entropy. So this is really important for cryptography. We would also need the sandwich Rene conditional entropies, which are defined this way for the purpose of this talk. The exact definition is not really going to be important. I guess the important fact is the fact that these things, they interpolate between the min-entropy and the von Neumann entropy, and that helps in deriving tight bounds. We also need the max relative entropy, which is defined this way, and the smooth version of the same thing, which is just like the smooth min-entropy. It just takes the infimum this time over a epsilon ball around the first argument. Okay, let's move on to something new, which is the approximation chains part of the talk. Okay, first of all, some notation. Yeah, okay, some notation. Whenever we have a subscript 1 superscript n during the course of this talk, it's going to represent the registers a1, a2, to an. But yeah, with that notation out of the way, let's consider a state rho a1 through np. For this state, we will define a sequence of states sigma k as an approximation chain of the state rho. If for every k, the partial state rho a1 through kb can be approximated by the state sigma k. And that's all there is to this definition. The cool thing about these approximation chains is that you can bound the von Neumann conditional entropy of the state rho using these approximation chains pretty easily. So yeah, whenever you have like a conditional von Neumann entropy, first write it out as a chain rule, as here. Then once you have that those quantities, you can just use the continuity bound for the conditional entropy to change your state from rho to sigma k's. And now you have something which looks like this, a bound in terms of the approximation chain of the state rho. Plus you also get like these small error terms, but it doesn't really matter because they're small. And if you further have that something like this holds true, then you get a linear lower bound on the von Neumann conditional entropy, which looks like this. This is great. This is actually the kind of thing we like doing in cryptography, except for the fact that you want the smooth min-entropy here instead of the von Neumann conditional entropy. So yeah, we have this thing with the von Neumann conditional entropy. We would love to see something like this for the smooth min-entropy, except for the fact that you can't see something like this for the smooth min-entropy because it can't hold true for the smooth min-entropy. There's very easy counterexamples which one can construct to show that this is not true. So what we do in this work is just to consider these approximation chains, but with additional assumptions so that we can make something like this hold true. That's it. Okay. So yeah, the first and the strongest and simplest assumption we could come up with is the approximate independence case. In this case, we assume that the sigma case will look like this. Okay, and what this essentially says is that the state row is such that every register AK for the state row is almost independent compared to whatever has come before. So the state AK, register AK is almost independent of whatever has come before, like this. Further, let's assume for simplicity that all of these registers AK, all of these states row AK are the same. And now the question becomes, how do we prove that the smooth min-entropy of A1 through N given B is large specific for this row, specifically that something like this holds true? So this f of epsilon over here, it's just some small function of epsilon. Okay, and something like this should intuitively hold true because everything is like kind of independent of one another. One thing to note here is that this epsilon in this smoothing parameter and the epsilon over here, they're the same epsilons. You cannot really get around the fact that they have to be the same. Okay, yeah, that thing. And what you really do not want is the function f of epsilon to depend on the parameter n. You want it to be independent of n. Particularly, you want to be able to take n to be arbitrarily large. Okay. What I'm essentially saying here is that this state row behaves essentially similar to this completely tensor product state, at least entropically. So yeah, let's just for fun try to calculate the trace distance between these two states. And if you do that, it's very easy to use the triangle inequality and show that this trace distance is going to be bounded by n epsilon. Now, this is the best you can do really, this or the fact that the trace distance is bounded by 2. And yeah, this is not good because like if n is large, then this is meaningless itself. So yeah, that doesn't really help. But the idea is that n epsilon is a bad bound for the trace distance, but it would be a great bound for, let's say, a divergence, an information theoretic notion of distance. So let's try to use that. And the way we want to use that is that instead of trying to use a metric-based triangle inequality, we will use some sort of an entropy-based triangle inequality. And what I mean specifically by that is that let's say you want to bound this smooth min-entropy of rho in terms of the min-entropy of another state theta. It's a completely different state. Let's say their smooth max divergence is d. Now, by definition, this implies that there exists some rotella close to rho such that it satisfies this operator inequality. That's just the definition of the smooth max divergence. Now you can further use the definition of the min entropy of eta to just get this bound. And what this essentially implies is a smooth min entropy bound for rho, which looks like this. Okay. So yeah, we have this, and we call bounds like these entropic triangle inequalities because you start off with some sort of entropy on rho, but then you want to change to a completely different entropy eta. And you do that by taking into account their distance, this distance, whatever it is. This can actually be improved to this thing that we have there. And the main improvement is the fact that on the right-hand side, now you have an alpha Rene entropy. Plus, you also need to like take the divergence into account this way. And then there's some constant term which never really bothers you, so don't think about it too much. Anyway, so this is implied by something which actually looks like a triangle inequality. And yeah, that's why like everything here is called a triangle inequality, because they're really all just divergences, right? Okay, let's get back to the original problem that we had, which was this thing. And because I talked about these triangle inequalities, it means that we have to apply them. The way to do that is to bound the smooth max distance between these two states, particularly this state, because I mean, it worked well with the trace distance, or like kind of seemed to work with the trace distance, so why not? Okay, bounding the smooth max relative entropy just seems too hard, so let's begin with the relative entropy first. Okay, when you write out the relative entropy this way, it looks a lot like mutual information. And well, okay, so in the mutual information case, you have like two tensor factors here, but now you have n plus one. Turns out that this is a well-studied quantity. It's called the multipartite mutual information, and it's related to the mutual information in this fashion. Okay, now once you have this equality, you can just use the distance bound that we have on top, along with the continuity property of the mutual information to get something like this. So this one is a small term. But the great thing about this one is that it's a mutual information over a tensor product, so it's equal to 0, and you get this bound. Now this is n times something small, which is exactly the kind of bound you needed, except that you needed all of this on the smooth max relative entropy. Now, if only there was a way to go from the relative entropy to the smooth max relative entropy, well, there is. It's called the substitute theorem. It's a very powerful tool. And it essentially says that in order to go from a relative entropy bound to a smooth Dmax bound, all you have to really do is divide the relative entropy by the smoothing error squared. Plus there are some constant terms, and you don't really need to care about these for the purpose of this talk. Okay, so you define like your smoothing parameter in the correct fashion, and you can show that the relative entropy bound that we have implies a smooth Dmax bound as well, which is great because now we get to use our entropic triangle inequality finally. And okay, so yeah, now you see that on the right hand side here we have some sort of conditional entropy on this completely tensor product state, which is really easy to evaluate because it's just going to be n times whatever the entropy of the first register is. And then the smooth Tmax term, it contributes like a small error term, which is okay because we're going to choose alpha equals 1 plus delta, and it's going to result in like a bound which looks like this. We also use like the continuity of the Renier entropy here to go to the von Neumann entropy in the final bound. And this is essentially what we wanted to achieve. So yeah, that's like one problem done. Okay, any questions up to this point? If not, I will move on. So let's look at some applications of. Oh yes.
So when you use the substrate theorem, doesn't that constant also add up in times, or I use the substrate theorem only once?
This one? Yes.
The C that you addition plus C that you have when you go from Dmax to the D, then you have like a plus C in the substrate theorem, right?
So
yeah, that's all done.
this small term,
Or is you use
you just use it once, you don't use it multiple times. The bad factor is actually this 1 over delta squared. It can actually be big if delta is small, but it's okay. I don't think, for at least this problem, you can declare it. So that's okay.
I have a question that's like before this.
Before this one?
One line down.
One line down, this one.
This second 2 and delta isn't that dangerous because delta has to be of the order 1 over n, and you have this O to the n cube.
This one?
Yeah.
That's
It's like huge, right? Because you get an n squared.
Oh no, that's a typo. Sorry. Yeah, my bad. That's just supposed to be 2 delta inside.
So there's no extra n here.
There's no extra in there.
Because that would have scared me.
Yes. My bad. Okay. Anyway, there needs to be some comedy in the presentation. That was it. Yeah, so one of the things you can do with the approximately independent registers bound is to create quick and dirty proofs of security for cryptographic schemes. So for example, for the sequential DIQ device independent quantum key distribution protocol, it can be shown very easily that there exists a winning threshold for the underlying CHSH games used in the protocol, such that if the protocol does not abort, then Alice's answer in the kth round of the protocol are going to be almost independent, almost random compared to whatever has come before, including the adversary's information. Because these registers AK are, okay, so this is a entropy-based way of saying the fact that AK is almost independent of whatever came before. You can also transform it into a trace distance-based way of saying the same thing. And now, you can use the smooth min-entropy bound we just came up with to show a linear lower bound like this. This is exactly the sort of thing you want to show for a protocol, for a cryptographic protocol like this. The problem with this approach is that it ends up linking the smoothing parameter and the winning threshold of the game. And you typically want the smoothing parameter to be really small, which would imply that the winning threshold for the CHSH games needs to be really close to the maximal winning probability. And this is really a bad protocol because it can't be implemented in practice. So yeah, this proof method still gives you a proof of existence type proof, but it's not a real world proof. Okay. So another application for whatever we just did is the source correlation problem. In QKD protocols, Alice, one of the honest parties, is required to produce a tensor product of states like this. So she's essentially, there are n rounds, and in each round she's required to produce this state. In theoretical proofs of QKD, it is assumed that she's able to produce this tensor product state, which implies that all of the rounds are independent of one another. But in practice, every physical device has some sort of errors, and it also has some sort of memory to it. And both of these things, they're going to end up causing different rounds, the state produced in the different rounds, to be correlated with each other. So the real state produced by Alice is just going to be some general rho. It's yeah, it can't be broken down into a tensor product like this. And yeah, it's going to be a very beyond IID state. So the source correlation problem is just how do you prove security for QKD when you're given such a state as a source? So we solve this problem in 2 ways. I'm going to show you the bad way of solving this problem because the good way requires like more work. Anyway, so yeah, for the bad way, we assume that the source satisfies these 2 assumptions. And what these essentially say is that the classical random variables used in the protocol are correctly produced. And the state produced by the source in the kth round of the protocol is almost correct, which is this one. Under these conditions, you can basically reduce this problem to the approximately independent register scenario. And importantly, you can prove a smooth max divergence bound like this. Now, the state in the second argument over here is just a tensor product of almost perfect states. The epsilon over here represents the fact that you need to add some sort of noise to the A registers so that the divergence doesn't become infinite. Okay, but the really interesting thing is what happens when you do the entropic triangle inequality on this thing. And this first term over here, it represents it is the smooth min entropy you need to bound in order to prove security for QKD. And it's evaluated on the state produced by the QKD protocol being applied to the real state produced by the source. Whereas on the right-hand side, we have the same alpha Rene entropy, but now evaluated on a state which is produced by the QKD protocol being applied to a source which produces these states. And because these are just the perfect states with some IID noise applied to them, it's fairly easy to use the existing QKD techniques to bound this term linearly. So that's great. And the smooth Dmax term is just going to, again, contribute something small that leads to like a small entropy loss per round. But yeah, I said this was the bad way of carrying out this solution. And that's because, again, because we're using the substrate theorem, it ends up linking the smoothing parameter with the source error. So you can't really make this arbitrarily small, which is what you like to do for cryptographic schemes. But there is a way of making this error arbitrarily small, and that relies on using the quantum sampling paper in order to bound the smooth Dmax instead of the substrate theorem. All right. So yeah, another approximation chain we study is the scenario of approximate entropy accumulation. In entropy accumulation, you begin with some, say, rho R naught E, and then you apply a bunch of maps MK to the R registers of the state, which produce some registers AK and BK. You can think of the registers AK as some sort of secret information, and the registers BK as some sort of side information which is leaked to the adversary. And then the entropy accumulation theorem just says that for the final state, which is this one, as long as it satisfies these n Markov chain conditions, we can bound the smooth min entropy of this state using this thing which looks like a chain rule itself. Okay. In approximate entropy accumulation, we just really want to relax these conditions a bit. The way we do that is by considering the same state, the same setting, sorry. But now let's just say that the maps MK themselves, they're not nice enough for this final state rho to satisfy the n Markov chain conditions. But instead, these maps MK, they are approximated by some other map NK. And let's say these maps NK, they satisfy all kinds of nice Markov chain properties. We'll pin down the exact properties they need to satisfy later on. But let's just say, to start with, that it's enough to go from the smooth min entropy of this state, which is really produced in our setting, to an alpha Rayleigh entropy on this state, which is produced when you apply the maps NK instead of the maps MK. Okay. So yeah, if you want to do that, we just need to bound the smooth max divergence between these two. Okay, so the first step over here is to just move to the alpha Rayleigh entropy, Rayleigh divergence of these two things instead of the smooth max divergence. The next step is to separate out the contribution to this entropy using the chain rule for alpha Rayleigh conditional entropies. Sorry, alpha Rayleigh relative entropies. And And yeah, that separates this chain rule, it separates this into two terms. One of them is a contribution because of the nth channels which are applied to the states. But why just do this once when you can do it n-1 more times and get this? Okay. So we do that, and at the end we have a summation like this, or summation of channel divergences. Now at this point, if we were able to show that each of these channel divergences were small, then we would get something like n epsilon at the end, and we would basically be done. But the thing is, just because two things are close to each other, it doesn't imply any sort of bound on their divergence. It's the same as the reason this is not true for states. Okay, so yeah, if that doesn't work out, let's just mix the channels nk with a little bit of mk and define some new mixed channels n delta k. For these channels, we can again just do whatever we did previously and derive the same bound, except now the second argument of the smooth max divergence is this state. And further, we don't want to deal with the regularized divergence. So we move to yet another kind of alpha Rene divergence, which is this sharp divergence. And it turns out that for this divergence, you can create the kind of bounds that we need. They're not great, but they work. So let's just move on. And for an appropriate choice of delta, they will give you something like n times something small, which is good enough. Okay, once we have all of this, we have the setup for applying the entropic triangle inequality. This divergence is small, so it's great. But okay, so we would really, at this point, we would really like to apply the entropy accumulation theorem to this entropy. But because the state eta is defined using the n delta k maps, and these maps, they mix the map nk with a little bit of the bad map mk, the state eta itself doesn't satisfy any sort of Markov chain conditions, as is required by the entropy accumulation theorem. But it still turns out that because you're in every round, you're independently choosing between the map nk and the bad map mk, and with overwhelming probability, you're choosing the map nk. Everything still works out using the same argument as entropy accumulation, and we are able to derive this approximate entropy accumulation theorem. So yeah, these are the Markov chain conditions which the maps n need to satisfy. And the main points of this theorem are that the smoothing error this time is arbitrarily, can be made arbitrarily small. That's great. The rate loss per round is, it's small, but it's like still bad. And the reason for that is the fact that our channel divergence bounds were bad. But if one of you can improve those divergence bounds, then this term also improves. Lastly, we also need some sort of a bound on the size of the side information. This is not a limitation of our technique. It turns out that this is necessary for proving a bound like this. Okay, that was all of the technical details that I had to give out. But if there's one thing I would like you to take from this talk, it would be that the entropic triangle inequality, I think it's a pretty powerful tool, and we will see some more applications of this. Then, yeah, I have a summary and some list of questions. I've actually never gotten this far in my practicing of this talk, so.
The time is also up.
Okay, yeah, so let's just stop.
So we can just leave it like that.
Yeah.